Hello, and welcome back to Chapter 11 on angular momentum. Question 14 is a relatively difficult question, and when you probably saw this formula right here, you said, wow, better watch the video. Well, you're in luck. So the question states, a conical pendulum consists of a bob of mass m in the motion in a circular path in a horizontal plane shown in 11.14. I'd really look at this picture, it really helps, but I drew it down there. The wire contains a length L, maintains a constant angle of theta with the vertical. Show that the magnitude of angular momentum around the circle is, L equals, well, 1/2 to the power of 1/2 is just a square root. So L equals the square root of m squared g L cubed sine to the 4th theta over cosine theta. So this is just great. So what we're given is L, theta, and m. We actually aren't given these values, but since they say them in the question, we're allowed to use them in the overall final answer, which is the proof. And what we're supposed to find is the proof. Alright, so the first thing I want you guys to look at is this picture right here. This picture is the picture drawn in the book, and what you can see is that this mass is tied by a string to a ceiling of some sort, and is spinning around in a perfect circle right there without losing any theta, or moving in the x direction, or moving up or down in the y direction. It's only moving in this circle, in the z direction, let's name it. So, since it's not moving in the x or y direction, this is where we're going to have to start. It's not moving to the left or to the right. It's not moving up or down. It's just moving in the circle, like this, in the third dimension. So what we can do is we can do one of these forces things where we see what's pushing it to the right, what's pushing it to the left, what's pushing it down, and what's pushing it up. Alright, so to begin, there's obviously a tension force going to right here, right? Going up and to the left. So this will have something to do with this force, something to do with this force. Alright, so let's start with this. What would be this up force? Well, the up force is just this line right here. And we know from geometry that cosine theta is equal to adjacent over hypotenuse. Alright, so the cosine theta is equal to this over this. So let's rewrite that as cosine theta is equal to the tension force, because this length is also the tension, is equal to, this is the adjacent, is, we'll just name that as adjacent, times the hypotenuse, which is the tension force. So we can automatically see that this adjacent line right here is equal to t cosine theta, which is very important. So in the upwards direction, we have t cosine theta. Similarly, pushing it to the right, or sorry, take that back, to the left is this line right here. We know from geometry that sine theta is equal to opposite over hypotenuse, or in this case, this would be tension. So we can rewrite this as the opposite force, this line right here, is simply equal to sine t tension sine theta. So in the left direction, t sine theta. But we know that if these were the only two forces, that according to Newton's first law, that this ball would just indefinitely move this way. So there has to be another force pushing it down and to the right. So what's pushing it to the right? Well, that would be the centripetal force. And we know that centripetal force is equal to mv squared over r. But wait a minute. Part of our given doesn't include this r. We're going to need to deal with that later. I just want you guys to look at that, because we can't leave that r in the final solution. First of all, it's not even there. But second of all, we can't leave it because it's not one of our things that we're given. In the downward direction, well, what puts everything down is weight. This ball obviously has a weight, so mg. So these forces are equal, and these forces are equal. So what we have to see here is we have two formulas already. T sine theta is equal to mv squared over r. T cosine theta is equal to force of weight. So we can actually divide these two formulas together. I was really surprised when I saw this my first time. I'm like, wow, you could divide two formulas together. And I thought that was nifty. Didn't really understand why, but accepted it, because that's what you have to do in physics. Just accept it. Alright, so we can divide these two formulas by each other. So I just took this formula, divided it. So the t's cancel out. I'll just write it right here. The t's cancel out. Sine over cosine was tangent. And we have mv squared over r divided by mg. So the m's cancel out, and we get tangent theta is equal to v squared over rg. Rearranging this, moving this rg over this way, square rooting it both, you get v equals the square root of rg tan theta. Alright, so this is pretty cool. We also know that angular momentum is equal to rmv, or the sum of rmv. But in this case, there's only one ball, so we only have to deal with one. So it would just be one anyways. So angular momentum is equal to rmv. But we already know that this v is rg tan theta. Remember, we were not given v. So that's why we have to make all these substitutions. Because we're really trying to put everything in terms of what we're given in the formula. So we get rm rg tangent theta. So a property you learned in Algebra 2 is that, or Algebra 1, I'm not even sure, is you could put this back in to the square root by making it the square root. So because r is equal to the square root of r squared, so what they did right here was they put it back in there and made it squared. So they took the square root of r squared times the square root of r to get r cubed, put the m back in there to make r squared of r m squared, g, tangent theta. But here's another problem. This r, like I was talking about earlier, that's not part of the given. So we need to make another relationship. And the relationship is that r is equal to L sine theta. So what you have to think about is that sine theta, or the r, is just this right here. This is r. So we obviously have to make some sort of relationship with L. And the relationship is L equals r sine theta. So now if we take this and cube it, because r is cubed, we get L equals m squared g L cubed. So I took this tangent theta and made it sine cubed over cosine cubed, because there's a sine cubed there. Made it sine to the fourth over cosine. And this is actually our overall formula. I'm going to refrain from running it to the 1/2 because it's the same exact thing. But as you can see, it's the same exact thing. So this is a very, very difficult question, and to actually get it by yourself is very difficult. So it's just practice is what it takes. Physics is just using formulas and using math and trying to figure it out to get to the end product. You're not expected to know this on the AP Physics exam. That would be insane. Just try your very best, get as far as you can each time, and just see how it finishes off. Physics is a learning experience, a crying experience, and a terrible torture to most children. Goodbye, friends.